So please.
Thank you very much for the introduction, and thank you very much for the invitation. Anna Tuschling told me so much about this project and how it came together that I'm very glad to be actually, I think, the first speaker here, and it's an honor to be here for starting this round of lectures. I've seen that you have invited other colleagues from Bochum, whom I also hope to meet in the future and couldn't meet in the last 2 years because of COVID. And I hope that we will also have the chance to meet in person in the next few months. I hope that you can hear me because my room is under the roof and it's raining a lot here in Berlin. So I hope it doesn't interfere with the lecture. 1 second. In recent years, adaptive autonomous technologies such as robots, drones, vessels, rovers, or cars have made enormous advances in terms of sensing, interacting, and finally also deciding based on environmental relations. The technological capabilities of sensors, algorithms, and machine learning are becoming more and more fine-grained with every development cycle, enabling more or less reliable, quick, and safe adaptive behavior in unpredictable environments. Particularly self-driving cars, or rather the advanced driver assistance systems that are installed in all new cars, are at the center of public interest, since they are an element of the current transformations of traffic and have the potential of fundamentally transforming the ways in which human beings and autonomous technologies interact. When digital, smart, and spatially distributed technologies with advanced sensorial capabilities, which are today often discussed under the rubric of the Internet of Things or of ubiquitous computing, capture surrounding spaces and interact with other objects, the time-critical processing of environmental relations becomes a central technical challenge. This is especially important in street traffic, where countless human and non-human actors encounter each other and must interact at high speed. Automating traffic places the highest level of demands on the time-critical processing of data, artificial intelligence, and the corresponding synchronization of movements in space. Autonomous systems must be able to cope with the unpredictability of the environment and react to potential events within the shortest possible time intervals. In traffic, time-critical decisions can be a matter of life and death. Such adaptive technologies have been described as autonomous in the sense that they are able to interact with their surroundings. They cannot be understood apart from their environments, since these surroundings are not passive conditions of behavior. Rather, the operation of these systems is based upon a technological ability to pervade relations with the environment. Autonomy is not meant in this case to be understood in the Kantian sense of the self-determination of goals and intentions, but rather, as I will explain later, as an effect of the complex interaction of human and non-human components on both sides of the environment system divide. These technologies possess what the philosopher Christopher Hubich calls operational and strategic autonomy. They are able to choose different means to reach a specific aim, but cannot determine their own goals. Obviously, they do not achieve moral autonomy. When I speak about autonomous cars, I do not intend to assign them a human-like autonomy, but rather the capacity to interact with the environment by means of what I suggest we call microdecisions. Using their sensors and respective filter algorithms, autonomous systems must be able to register events and objects in their proximity, locate and situate themselves in relation to them, project their own behavior into the future, build world models, and on this basis decide upon actions, reactions, and interactions. This development raises questions about how such technologies manage both the unpredictability of the environment and the complexities of interaction with human and non-human entities. It consequently also raises questions about the conjunction of environmental sensors, data analysis, and the procedures of decision-making that are required to operate under conditions of uncertainty. In this lecture, I will present the concept of microdecisions as a heuristic tool to overcome the challenge of describing the time-critical interaction of autonomous machines and other actors. By focusing on how adaptive technologies model their environment in order to interact with it, I will argue that microdecisions, that means the sheer number and speed of operations based on algorithmic processes, constitute the operationality of technological adaptation to constantly changing environmental conditions. The technological power to choose between options of behavior is based on an alternativity of possibilities, which in the case of autonomous cars are generated in the process of building virtual world models. From a media theoretical perspective, the question arises as to how such options and alternatives of possible behavior can be technically generated. For autonomous technologies, they are never given, but rather depend on the calculation of virtual world or scene models based on algorithmically filtered sensor data. As I will show, these models consist of nothing else than pluralities of probabilities. Technically, models such as the one you see here in a visualization made for human eyes are not representations of the world, but more or less fine-grained resolutions of the probabilities of environmental factors that are relevant for the vehicle's action. Only in reference to these probabilities and their plurality, it makes sense to speak of decisions. Decisions require the availability of options, what I'm suggesting we call alternativity. As it will turn out, the generation of alternativity is strictly bound to the environmental relations of the car and the processes of world modeling. Before I go into details, please let me start with some general remarks. Microdecisions are not strictly defined protocological procedures. They do not designate a specific method. As an alternative category of analysis, the term illuminates a connection that would remain invisible if one were to use only technical or mathematical vocabulary. It refers to a certain perspectivization rather than a concrete object. But microdecisions are also not simply an observer's construct. They are an effect of a constellation of microtemporalities, algorithmic categorizations, and data analysis that has become prevalent in a range of different contexts. Microdecisions decide upon options for possible solutions and potential worlds. They become effective because they circumvent human restraints and can only be processed in large numbers on a microtemporal scale. They are no algorithms, but an effect of their implementation. In the examples presented here, their conditions consist in the need to decide in extremely short time spans the microtemporal processing of data and the givenness of alternativity. Their scope becomes particularly evident in the context of technologies whose algorithmic capacities are used not only for static calculations of solutions, but also for time-critical localization, orientation, and movement of objects within space. This conceptual framework makes clear that the way in which autonomous adaptive technologies interact with their environments necessarily entails political questions about sovereignty and the autonomy of the automaton. The politics and biopolitics of autonomous technologies consist in keeping alternatives open and not being determined in advance. The temporality of microdecisions is decisive and critical in the sense of crisis, as the moment of decision from Greek krinein for deciding, and it is thus political. Microdecisions thus constitute a new mode of power and decide upon possibilities that determine life in digital cultures. Who can move where and who cannot, who is connected and who is not, who survives an accident and who does not. The politics of microdecisions thus inevitably raise questions of sovereignty as the power to decide in digital cultures. The machines that carry out microdecisions are of course produced and managed by humans who also program the machine's algorithms. The specifications according to which decisions are made are necessarily established in protracted institutional, legal, and political negotiations. Microdecisions are thus always complementary to institutional and collective macro decisions about appropriate behavior and meso decisions of individuals in specific situations. These rules can then be applied to new situations depending upon the pre-given goals defined beforehand in macro decisions, for example, that the safety of pedestrians is more valuable than the safety of passengers. Micro decisions are necessarily calibrated for and judged on what happens on the road, but they are located at a different operational level from either political intervention or technical implementation. They are effective precisely because they bypass the time-consuming act of human decision-making. And in this sense, I will describe these decisions taking the perspective of the machine. And one final remark, the act of deciding between options, even if it is based on algorithms, cannot be explained by making exclusive appeal to algorithms. The operational function of alternativity requires a different approach, one that explores algorithms, but does not understand algorithms as explanations in themselves. Rather, what needs to be explained is how algorithms achieve the power to decide and why decisions are always more than algorithmic. Hence, when I apply the concept of decision, one traditionally associated with an intentionality, to microtemporal processes below the threshold of consciousness, I do so to explain the necessary openness of autonomous behavior and interaction. Openness in the sense of having two or more options. It is important that these decisions can always be made differently and are therefore not immutable. The potential of the politics of microdecisions lies precisely in this difference. To become decisions, microdecisions need alternatives. And the givenness of alternativity and the technical creation of alternativity is a necessary aspect of the probability calculus of technologies of what is called world modeling in robotics. The Society of Automotive Engineers distinguishes between 5 levels of automation with different degrees of autonomy. With the basic driver support features of level 1 and 2, advanced driver assistance systems can accomplish limited tasks, although the driver must constantly supervise the car. At level 1 in what is called hands-on mode, at level 2 in hands-off mode. Advanced automation starts at level 3, in which the car is able to regulate its behavior autonomously in specific situations of eyes-off mode. At level 4, in a mind-off mode, the driver can focus on something else, and at level 5, there is no need for a driver, steering wheel optional. The degrees of automation in today's cars range from collision avoidance systems or lane assistance at level 1 and 2 to recent prototypes of autopilots entailing a suite of interconnected advanced driver assistance systems for highway usage at level 2 or 3, and the first driverless shuttles at level 4 being operated commercially, for example, by Waymo in strictly geofenced areas in Arizona and California. Whether or not the use of fully autonomous vehicles on level 4 or 5 will ever be viable in all areas of the world is a matter of debate. And since 2019, more and more companies have begun to withdraw their market predictions as the complexities of the task have become clearer. Nonetheless, even if autonomous systems are not yet capable of totally replacing the driver, the relevant hardware is already installed in millions of cars and new software is constantly being developed. All advanced driver assistance systems and their complex interrelations are meant to optimize interactions with the environment, but the environment with which an autonomous system operates is never a given and isomorphic representation of the world. Rather, at least for more complex combinations of driver assistance systems on higher levels of automation, the environment is a fragmentary and operational model that has been created by a specific correlation of sensors with different capabilities, of filter algorithms that analyze sensor data, of processes of machine learning that optimize pattern recognition, and of operating decision modules. By focusing on this intersection of different technologies, my presentation explores the epistemological constellation in which the autonomous car's environment is constituted by processes of world modeling that, as I will show below, incorporate probabilities that are fundamental for microdecisions. A model of the car's environment is the basis of numerous decisions to solve specific situations. braking or not braking, turning right or left, changing lanes or not, and in the future, perhaps even passing another vehicle or not. These acts cannot be understood solely as the execution of deterministic algorithms that always provide the same output with the same input by specifying a threshold at which a defined reaction must be triggered in the case of a specific event. Nor can they be explained by reference to an instance of consciousness that decides on the basis of knowledge, experience, or perception. Rather, if we stipulate that autonomy in this context means that a car is able to adapt to environmental challenges, then any conception of algorithm-based solutions becomes problematic. Autonomous systems need to have a multiplicity of exit points linked to specific sequences of interaction. Exit points are facilitated by algorithmic if-then conditions that evaluate external data compiled by sensors. To take an algorithmic view implies that the system is exposed to the same conditions, that if the system is exposed to the same conditions, it will react in the same way. However, in a car, an autonomous system must be able to respond to all relevant events in the environment. Its autonomy requires that there be several options open to it. Otherwise, the system would be deterministic, not operationally or strategically autonomous, and would not be able to adaptively adjust to unpredictable and unsafe environments. The algorithms of autonomous systems include probabilistic models because deterministic responses for all scenarios are, in fact and in principle, impossible. The unpredictability of the environment necessitates a probabilistic approach to algorithms that allows for self-adjustment and can have multiple inputs, for example, neural networks or Bayesian networks with decision trees that determine different outcomes based on the states of the system. Consequently, it becomes difficult to conceive of autonomous decision-making as the transformation of an input into output. Nonetheless, as I want to argue, it is important to describe these processes on a different level because microdecisions cannot be epistemologically reduced to algorithms. Decisions require time. If a decision happens immediately, it would have been decided in advance and it would be deterministic. Temporality is thus key to understanding how these technologies operate. The temporality of microdecisions is an effect of the sheer mass of calculations and the speed of automated processing. Microdecisions exceed human capacities because their numbers and their speeds can only be accomplished by computers. Their quantity is their quality. The algorithmic processes that underlie microdecisions can in principle also be performed by humans because as formalizations, algorithms can be processed by a machine or by a human at any speed with exactly the same results. By definition, time is not critical for algorithms, only for the technologies that apply them. An algorithm returns the same results regardless of whether it is processed by a human brain or by a digital computer, of whether it takes a microsecond or an hour. But the medium-specific speed and quantity of microdecisions are not substitutable. Time is critical for microdecisions. As all computational processes, they only become effective when processed in times and quantities that are inaccessible to humans. If decisions are drawn in this microtemporality, it becomes necessary to negotiate what it means to decide and to be sovereign. To explain this microtemporal dimension of automated decision-making and the reciprocal and recursive entanglement of autonomous technologies with their environments, I would like to provide an example that helps reconstruct the framework of alternativity underlying microdecisions. In September 2016, the car manufacturer Tesla released update 8.0 for the operating system of the onboard autopilot limited to highway applications. The update included a new algorithm for processing the signals received from the vehicle's built-in radar. The fact that Tesla speaks of an autopilot is not to be mistaken as evidence of self-driving capabilities at level 3 or 4. Rather, autopilot means here the combination of different assistance systems, collision warning, auto steer lane centering, self-parking, automatic lane changes, and adaptive cruise control. In this regard, Tesla offers a good example of the constraints and challenges and potentials of driving assistance, although it is certainly not the only competitor in the field. Manufactured by Bosch, the mid-range radar sensor, which is mounted on the underside of the car, is also used by other automakers. Tesla, though, was the first company to introduce a new feature. With algorithms optimized by machine learning, the onboard processor of the car extends its potential of data analysis to the motion of the car driving in front of the car driving in front of the Tesla. Beginning with this update, the system uses the fact that the radar signal is reflected between the underbody of the preceding car and the road surface to detect the approximate shape and movement of objects in front of it, even if they are invisible to the driver and the car's visual sensors. This new application does not rely on improved hardware, but on optimized algorithmic processing of available sensor data. It extends the car's reaction radius to events that are invisible to the driver. This implies that the temporality of the intervals of intervention between the car and the driver do not coincide. 2 months after the update, a high-speed accident occurred between two non-Teslas on a motorway in the Netherlands, fortunately without any injuries. A dashcam in an uninvolved Tesla Model X recorded the accident. The video, which the driver published online, shows how the Tesla's onboard autopilot reacts to the imminent collision of the two cars in front of it, even before the collision takes place. I will show the video a second time. The Tesla brakes automatically before the driver even has the chance to recognize that something is going to happen, let alone intervene. A warning signal can be heard in the video, and the car starts to slow down, but at this moment, nothing unusual can yet be seen on the highway. Seconds later, we realized that the Tesla has, by means of the new algorithm, predicted the collision before it happened, calculating the speed and movement of the vehicle that was two cars in front of the Tesla and thus invisible to the driver. Had the Tesla not responded automatically in this short interval, it might have driven directly into the resulting accident. And I'll show it once again. This interval of intervention is accessible only to the car and not to the driver. Only after the event do we understand that the time to react was not only below the threshold of human attention and responsiveness, though the driver could potentially anticipate the event, but that the driver could not have reacted because he could not see anything. The car, on the other hand, anticipates an accident that will only be visible to the driver in its consequences. In other words, the interval of intervention of the car and the driver do not overlap. The car's algorithms calculate the likelihood of a future in which it would be involved in the accident, and in an extremely short time span, far shorter than any possible human response time, it must decide, based on sensor data, between this future and a response that will help avoid this future. The autonomous car brakes before the accident even happens, let alone becomes visible to the driver. It responds to a potential event because its assistance systems compare the speed and direction of all three cars, calculating the likelihood of the accident and reacting accordingly. This reaction results from a deterministic consequence of the calculation of the probability of the collision. The algorithms are deterministic in their process. That means they always deliver the same input with the same output with the same input. Hence, if the threshold is exceeded, the driving assistance systems, depending on other variables such as weather, road surface, cars driving behind it, initiate the braking process. In spite of the givenness of the reaction in this scene, it must be possible in principle for a decision to be different, because only then would the autonomous system be able to interact with an environment that continuously demands new adaptations of behavior. If the vehicle had no alternatives, it would not be able to respond to and interact with its unpredictable environment. Its autonomy necessitates not only several exit points, but an openness towards other options and an implementation of a probability calculus on the level of its technical architecture. The key questions are where, in such a process, microdecisions are drawn, how alternatives are created technically, and how alternatives are compared to each other. In the following, I will try to answer these questions by referring to one specific architecture of autonomous systems. There are other architectures, but the examples described here allow to further refine the heuristic of microdecisions. To understand how autonomous vehicles interact with their environment and thereby project the alternativity that underlies microdecisions, it is important to distinguish between a strategic, a tactical, and an operational level. This subdivision and the corresponding illustration were developed in the context of a research project on the architecture of self-driving cars at the Technical University Braunschweig. The three levels correspond to the top three rows. Below that is the level of sensor-based data acquisition. And while the strategic level is concerned with the navigation of the car between two locations, and the operational level is concerned with the execution of driving maneuvers, the tactical level encompasses methods of locating the car in its surroundings and analyzing the situation. Algorithms are inevitably involved at all three levels. At the strategic level, they consist, for instance, in calculating routes, and at the operational level in steering and maneuvering the vehicle. But at the tactical level, algorithms are used to create probable models of possible worlds and corresponding options for action. The figure shows how sensor data flows into the feature abstraction and model-based filtering module, and from there further into context and scene modeling and road-level environmental modeling. On the left side, among the externally supplied data, which includes street maps or traffic reports, there are three levels of world modeling. Modeling, whether worlds or scenes, in this context is not the complete representation of the outside world in the mind of the machine, as it were, but the assembly of fragmented sensor data into a viable, that means operable, model of the environmental factors relevant to the system. For example, LiDAR, or light detection and ranging, uses point clouds of lasers that accurately capture three-dimensional models. LiDAR has a limited range, but it determines the contours of nearby objects by the measurement of the distance to these objects, while optical cameras are unreliable in close-up situations but provide a long range. In this regard, each sensor technology collects data constituting a sensor-specific environment, and this data can then be merged with data about other environments. This process is called world modeling. Depending on the equipment of the vehicle, the applications range from the calculation of distance to other road users to 360-degree modeling, as in this example. In order to move in the complex environments of road traffic, an autonomous vehicle must continuously register the states, the shape, position, and movement of the surrounding objects and locate itself in relation to them. It does not have access to a view from outside, but must constantly recalculate its own location and possible reactions to its environment. Since both the vehicle and other road users are mobile, the environmental relationships are constantly changing. Because the vehicle cannot know which position it is currently in, neither its location nor its relationship to other objects are given. In other words, the technical challenge consists of a safe approach to the uncertainty of the environment combined with the unpredictability of the behavior of other road users. Safety in dealing with this double uncertainty of the system over its own state as well as the environment is a key component of the strategic and operational autonomy of the vehicle. The problem of environmental orientation that I'm raising here was discussed in robotics and artificial intelligence research around 1990 under the name of simultaneous location and mapping, or SLAM. This research posited that the initial condition of a robot is its lack of information about its environment. This environment can be mapped only by moving and collecting data with the robot's available sensors, but these sensors are prone to error. All the data that the robot registers about its environment is relative to its own position and therefore dependent on its location, which in turn is needed to locate itself on the map that is to be created. As the robot moves and measures its environment, both at the point of origin and during movement, it acquires different sets of data about the environment depending on its positions and the available sensors. These data sets can then be compared by probabilistic techniques that broadly fall under the rubric of Bayesian filters, named after the 18th century mathematician Thomas Bayes. This results in probability values for the new position of the robot, as well as for the shape, position, and movement of surrounding objects. That means that everything that we see here in this example is not a representation, but is a value of probability for an object to be at this position. All data collected by the robot is relative to its position, and its position can only be estimated in relation to the environment. In short, in order to locate itself, the robot needs a map, and to create a map, it must locate itself. The tasks can only be solved simultaneously, and location and mapping are inseparable. On the basis of the collected data, an always fragmentary map or model is constructed. This map contains probability values, and it is a construction of a possible but probable world. Because of the SLAM problem, the world or scene model consists of nothing other than probability values about the attributes of the environment. These methods mark a conception of the environment as technically permeated by uncertainty. This uncertainty has two components. It means both the robot's ignorance regarding its own position and the unpredictability of the environment's dynamics. This duplication of uncertainty is the epistemological core of this process of simultaneous location and mapping, and the framework for the interaction between the car and the environment. Based on data about environmental relations, the central processing unit of the robot calculates, through mathematical filters, the probability of the possible positions and movements of tracked objects in space. Algorithmic filters are based on the comparison of sensor data collected at different positions and at different times. The superimposition of these data results in probabilities. Roughly speaking, the analysis of sensor data is accomplished by calculating probable attributes of the environment, as well as the dynamics of the movement by means of Bayesian filters from the measured distances and contours of objects at different times in relation to the robot. A Bayesian filter compares the model of the environment at the time t-1 with the sensor data measured from another position at time t. Referring to the superimposition of both measurements, the robot calculates the probability of its localization as well as of objects in the environment. Since the present t can always turn out to be different from the future calculated from the past t-1, this probabilistic approach corresponds to the virtuality of a possible but probable world. The identification of specific objects, such as children or traffic sites on the roadside, as well as the calculation of appropriate responses predominantly undertaken by optical cameras and algorithms optimized by machine learning, are only a secondary step to this virtualization of the environment. As it turns out, world modeling is itself an act of calculating probabilities. As a model of probabilities, the vehicle's world model is virtual in the sense that each probability encompasses a multiplicity of alternative futures. World modeling, in the context of such technologies, is always the modeling of possible worlds that are merged in a single model that contains them virtually. The complex sensors of these technologies are not focused on the mapping of an ontology in which all objects are registered on the basis of given coordinates as on a virtual map. Rather, objects are registered by the constantly changing relations of a virtual environment, including probabilities and improbabilities. This virtuality is transformed into an operational model, which in turn enables time-critical interaction based on microdecisions that are bound to probabilities. Out of the mass of probabilities, these decisions choose the probabilities that are relevant for the car and necessitate specific behavior. Autonomy in this context is the capacity to create virtual alternatives and to choose options. It necessarily depends upon technologies that bring forth these options and thus instantiate microdecisions. The double approach replaced the need for an a priori topological map and allowed maneuvering and navigating even in rough terrain or in the presence of other road users whose behavior cannot be predicted. In this sense, the world model is virtual and operational at the same time. It is bound to a multiplicity of futures of possible states and events, while this alternativity is the basis of microdecisions in the present. By means of this virtuality, in which probability and possibility are coupled to each other, the past is evaluated to anticipate the future and to make time-critical decisions in the present that allow or prevent this future. In this sense, the virtual environment created by these technologies is directly interwoven with the adaptive capabilities of the car. Due to its probabilistic modes of operation, the vehicle works with world models that could always be different, thus opening possible and therefore potentially different decisions. This openness is the basis of its relational entanglement with the environment. Alternatives are intrinsic to probabilities because probabilities implicate both what might be and what might not be. These alternatives are the prerequisite of microdecisions that are always located at the tactical rather than the operational level of autonomous cars. Not only is this virtuality the basis of decisions, but it carries their temporality and quantity in itself. In this context, every quantified possibility of a state or event in the environment incorporates a microdecision. It is in this regard that the virtual sensor-based and algorithmically computed modes of the environment, models of the environment created through SLAM, differ radically from other models and simulations. Microdecisions are not external procedures that are excluded independently of modeling. Rather, they are immanent to the autonomy of the system because, in this context, they are made on the basis of these probabilities. And I would like to invite those of you interested in the details to my inaugural lecture on April 27th, where I will concentrate on these questions in regard to the Mars rover Perseverance. This lecture set out to explore the adaptive capacities of autonomous technical systems in complex environments. It encountered the problem that the common vocabulary of algorithmic processes, even if they contain probabilistic elements, is not well suited to describe the complexity of world modeling based on sensor data and filter algorithms. Instead, it proposed the term microdecisions to grasp the non-determinateness that is necessary for adaptive and interactive behavior in a constantly changing environment. In the final section, I would like to draw some more general conclusions about the theoretical consequences of this change in conception. Oops. Sorry. Microdecisions are not associated with individual decision makers. Rather, they are effective precisely because they take place automatically in incomprehensible numbers and as quickly as possible, according to a fixed set of rules. The act of microtemporal deciding is not bound to a sovereign decider, but is located at the intersection of sensor data, filter algorithms, and the resulting probabilities. From this perspective, the complexity of the adaptive entanglement of autonomous technologies with their environments and the recursions in which both sides are linked is the starting point of a description that refuses to treat the environment as passive material that is subject to active processing of the autonomous system. Rather, they are bidirectionally coupled by microdecisions that constitute and draw on the probabilistic model. It would be a mistake to understand the microdecisions of autonomous automata merely as an implementation of what has already been decided, because in this case, the virtuality that is the basis for the operation of microdecisions falls out of view. The concept of virtuality adapted here makes it possible to describe the status of a model that is neither actual nor potential, but rather probabilistic. Because it is probabilistic, however, this virtuality contains the possibility of its improbability. The state or event could also prove incorrect or non-existent in the future. Such automata are open to different possible options between which they have to decide without being sovereign in the sense of an intentional subject. If an autonomous car gains sovereignty, in the sense that even momentarily it subjects others to its sovereignty, as opposed to being subjected to the will of the driver, this transformation of agency entails many political questions about platforms, digital capitalism, infrastructures, and the economies of distributed and stacked technologies. So this means that even though these automata lack both intentionality and sovereignty in any strong sense, their decision-making depends on complex configurations of technologies that create a multiplicity of possible worlds. Such decision-making capabilities need to be explained without recourse to concepts of intentionality and intentional sovereignty. In fact, they challenge the binarisms within which these concepts are embedded. In this sense, microdecisions are not the implementations of what has been decided, but rather are characterized by an openness to the contingent that cannot be grasped in purely algorithmic terms. A decision presupposes that there are alternatives between which one chooses. This openness, which legitimizes the concept of decision, does not mean that a decision could be made freely. Openness is not in opposition to determinateness. Rather, the alternatives that are open to microdecisions are part of a non-deterministic path dependency with different exit points. Alternativity is the result, but not the condition of the technologies of environmental adaptation. The assumption of a determination of decisions through machinic processes leads to a simplified distinction between the determinate agency of the machine and the free agency of humans. In order to prevent such shortcomings, it is important to examine the demands and expectations of foreseeable behavior associated with an instrumental understanding of computability and algorithms. In this regard, I have presented the first steps towards a new conception of microdecisions and environmental adaptation. The concept of microdecisions allows us to attribute agency and autonomy to these technologies without at the same time assigning them responsibility, which remains situated where macro decisions are made. The important ethical questions that arise with the automation of traffic should be asked with this perspective in mind. What I offer is an alternative, non-technical language of description that, while taking algorithms into account, enables a vocabulary that recognizes the unintentional sovereignty, temporality, and medium specificity of machinic decision-making. In other words, in order to understand how autonomous technologies shape the world in which we interact with them, we need to overcome the assumption of their passivity, their lack of agency, and their determinateness. To simply delegate decisions to machines and then to conceive them as determined algorithms, as something that necessarily happens as it happens, is at core a depoliticizing act. In this regard, it is the task of critical humanities to politicize machines. This means to take the alternatives of each decision, be it fast or slow, as a starting point. Such a discussion should understand automata not as sovereign, but as decisive. As deciding automata, they achieve unintentional sovereignty. In this sense, we should look at the implementation of standards of decision-making through sensor algorithmic virtuality and the ambiguity of the probable, without explaining the technologies in question as simple performing agents or lapsing into the desire for an instrumental understanding of algorithmic computability. Automata, their environmental relations, and their interactions cannot be so conceived. Decisions have a non-computational dimension, even if they are processed by computers. Thank you.
Thank you very much.